Imagine looking up at the night sky and realizing everything you see is just a tiny fraction of what's really out there. The universe is a vast, ever-changing stage where cosmic events unfold on scales so grand they defy human comprehension. And right now, astronomers are tracking something extraordinary: 25 celestial phenomena predicted to happen soon. Events that could rewrite the rules of space and time as we know them. Some of these cosmic spectacles will be visible from your backyard, while others will challenge the very limits of our scientific understanding. But one thing's for sure, they are all pieces of a puzzle that could reveal secrets about the universe we've only dared to dream of. Think about it. In the next few years, we might witness stars colliding in explosions brighter than entire galaxies, rogue planets drifting through the void without a sun to call home, or even the birth of new black holes in distant corners of space. These aren't just abstract concepts, they're real, unfolding dramas that astronomers are preparing to observe with bated breath, and the implications. They could redefine everything from the fate of our solar system to the fundamental laws of physics. It's like watching the universe write its own history, and for the first time we've got front row seats. So what exactly are these events, and why should you care? Because this isn't just about distant stars or far-off galaxies, it's about our place in the cosmos. Every one of these predictions holds clues to questions we've asked for centuries. Are we alone? How did the universe begin? And what lies ahead for the fabric of reality itself? Whether it's a once-in-a-lifetime supernova or a mysterious signal from the edge of space, each of these 25 cosmic events is a story waiting to be told. And that's exactly what we're going to explore step by step, wonder by wonder, as we dive into the most breathtaking phenomena soon to light up the skies. Buckle up, because the universe is about to put on a show unlike anything you've ever seen. Right now, one of the brightest stars in our night sky is on the verge of a spectacular demise, and it could happen at any moment. Betelgeuse, the fiery red shoulder of the Orion constellation, isn't just another twinkling light above us. It's a ticking time bomb, a massive supergiant star running out of fuel, destined to explode in a supernova so powerful it could briefly outshine the moon. Picture this: a sudden, dazzling point of light blazing in the heavens, visible even in broad daylight, casting faint shadows on the ground. This isn't science fiction, it's a real cosmic event with a front row seat for everyone on Earth. What makes Betelgeuse so special? For starters, it's one of the few stars close enough and big enough for us to witness its death throes in vivid detail. At around 600 light-years away, its explosion won't threaten Earth, but it will give astronomers an unprecedented opportunity to study the final moments of a supergiant star up close. The data collected could unlock secrets about how heavy elements, like the gold in your jewelry or the iron in your blood, are forged in these violent stellar explosions. Some scientists even speculate that Betelgeuse's core might collapse into a neutron star or a black hole, offering a rare glimpse into the birth of some of the universe's most mysterious objects. But here's the million-dollar question: when will it happen? The truth is, soon in cosmic terms could mean tomorrow or 100,000 years from now. Stars like Betelgeuse don't follow human schedules. However, recent dimming events and strange fluctuations in its brightness have astronomers buzzing. Some think these could be early warning signs, like a star coughing before its final breath. If it does explode in our lifetime, the spectacle would be unlike anything witnessed in recorded history. Ancient humans saw supernova, like the one that created the Crab Nebula in 1054, but never one this close, this bright, with modern telescopes trained on it. And what about the view from Earth? For weeks, maybe even months, Betelgeuse's supernova could glow as bright as a crescent moon, turning night into an eerie twilight in some places. It would be a once-in-a-civilization event, a celestial showstopper that poets, scientists, and stargazers would talk about for generations. but beyond the awe, the real gift would be the science. This explosion could help us refine our models of stellar evolution, test theories about cosmic radiation, and even reshape our understanding of how stars seed the universe with the building blocks of life. So keep your eyes on Orion's shoulder. Betelgeuse's grand finale isn't just a distant possibility, it's a reminder that the universe is alive, dynamic, and full of surprises waiting to unfold. And when it does happen, you'll want to be outside, looking up, witnessing a cosmic event that bridges the gap between the distant heavens and our own tiny corner of existence. When Betelgeuse finally explodes, the fireworks won't mark the end. They'll be just the beginning of a cosmic transformation. That brilliant flash will fade, but what's left behind could rewrite our understanding of stellar remnants. If the star's core collapses into a neutron star, we'd witness the birth of an object so dense, a teaspoon of its material would weigh as much as a mountain. Imagine a city-sized orb spinning furiously, beaming radiation like a celestial lighthouse, a pulsar. Astronomers would scramble to study its behavior, watching for telltale pulses of radio waves that could reveal secrets about matter crushed beyond recognition. There's another possibility, though one that's even more enigmatic. If Betelgeuse's core is massive enough, it might vanish entirely, collapsing into a black hole. Unlike the explosive spectacle of the supernova, this transition would be eerily quiet. The core's gravity would become so overpowering that not even light could escape, leaving behind an invisible pit in space. Yet its presence wouldn't go unnoticed. Scientists would monitor the surrounding gas and dust for signs of distortion, like space itself spiraling down a drain. This could give us the clearest look yet at how black holes form in real time, not from simulations or distant observations, but from a nearby star's final act. And here's where it gets even more fascinating. The debris from Betelgeuse's explosion will become a laboratory for cosmic chemistry. Supernova are cosmic forges, scattering elements like oxygen, carbon, and iron across space, ingredients that someday might form new stars, planets, or even life. By analyzing the light filtering through this expanding cloud, we could trace how these elements mix and evolve, piecing together the recipe that builds galaxies. It's like watching a bakery open in deep space with stardust as its flour. For astronomers, the real prize lies in the unexpected. Betelgeuse's death could challenge everything we think we know about supernova. Maybe it'll produce a gamma-ray burst, a beam of energy so intense it could strip atmospheres off planets light years away, though thankfully we're at a safe distance. Or perhaps it'll defy predictions entirely, behaving in ways no model anticipated. That's the beauty of cosmic events. They don't follow scripts. Every anomaly, every surprise is a clue waiting to be decoded. So while the explosion itself will be breathtaking, the aftermath, the decades of discovery it unlocks, will be the true legacy. This isn't just a star's death, it's a window into the forces that shape the universe. And for the first time in history, we'll have the tools to witness it all unfold, from the first blinding flash to the quiet birth of something new in the darkness. While Betelgeuse's explosion will be a fleeting cosmic flash, there's another event unfolding on a timescale so vast it dwarfs human history, a slow-motion dance of galaxies that will reshape our corner of the universe. 4 to 5 billion years from now, the Milky Way and Andromeda, two cosmic titans, will begin a gravitational embrace, merging into a single, colossal galaxy. Picture two swirling masses of stars, gas, and dark matter, each containing hundreds of billions of suns drawn together by an invisible force over eons. The result, a celestial mashup astronomers have dubbed Milkomeda, a name that sounds almost playful for an event of such staggering scale. Here's the surprising part. Despite the apocalyptic imagery of galaxies colliding, individual stars are unlikely to crash into one another. Space is so overwhelmingly empty that even during this merger, the distance between stars will remain vast. Imagine two crowds of people scattered across continents, slowly drifting toward each other. The groups will merge, but the chances of any two individuals bumping shoulders are practically zero. That's the reality of galactic collisions, full of dramatic motion, yet eerily peaceful for the stars themselves. What will the merger look like from Earth if our planet still exists by then? Over billions of years, Andromeda, currently a faint smudge in our night sky, will grow larger and brighter as it approaches. Eventually, its spiral arms will stretch across the heavens, warping and twisting under the Milky Way's gravitational pull. The two galaxies will pass through each other multiple times, like phantoms in the night, before settling into a new elliptical shape. During this cosmic waltz, clouds of gas and dust will compress, triggering bursts of new star formation fireworks on a galactic scale. The aftermath will be a universe unrecognizable to today's astronomers. Milkomeda's core will likely host a supermassive black hole duo, a binary system born from the merging of Andromeda's and the Milky Way's central giants. Over time, even these black holes will spiral inward and collide, sending ripples through spacetime itself. Meanwhile, our solar system, if it survives, could be flung far from the galactic core, drifting in the outskirts of this new hybrid galaxy. But here's the real mind-bender. This collision isn't some hypothetical scenario. It's already in motion. Andromeda is racing toward us at 250,000 miles per hour, a trajectory set by gravity itself. Telescopes have even caught glimpses of other galaxies undergoing similar mergers, giving us a preview of our distant future. These cosmic crashes aren't destructive, they're creative forces, recycling material and birthing fresh stellar generations. So while we won't be around to witness Milkomeda's birth, its inevitability reminds us that the universe is in constant flux. Galaxies grow, collide, and evolve, a cycle as old as time. And in that grand timeline, our Milky Way's fate is just one thread in an infinite cosmic tapestry. While galaxies collide over billions of years, our own sun is gearing up for a spectacular show on a much shorter timeline, one that could light up our skies and shake up our technology. Solar Cycle 25 is racing toward its peak in 2025, promising a fireworks display of solar flares and coronal mass ejections unlike anything we've seen in over a decade. This isn't just about sunspots, it's about raw cosmic energy slamming into Earth's atmosphere, with consequences ranging from breathtaking auroras to potential satellite blackouts. During a solar maximum, the sun's magnetic field becomes tangled like a ball of yarn, unleashing bursts of charged particles into space. When these particles collide with Earth's magnetic field, they ignite auroras so vivid they've been mistaken for city lights. Imagine stepping outside to see the northern lights shimmering as far south as Florida or Spain, a celestial light show visible to millions who have never glimpsed it before. But the spectacle comes with a catch. These same particles can scramble satellite signals, disrupt GPS navigation, and even knock out power grids. In 1989, a solar storm plunged Quebec into darkness for 9 hours without warning. The real wildcard, the chance of a Carrington-level event. Back in 1859, a solar superstorm sparked auroras so bright, people could read newspapers by their glow at midnight. Telegraph operators reported sparks leaping from their equipment, a glimpse of what might happen today to our far more delicate electronics. A storm that powerful now could cripple global communications for weeks, frying transformers and knocking out internet cables under the ocean. The odds are low, but the stakes astronomical, yet there's a silver lining. Modern science gives us a fighting chance. Networks of satellites now monitor the sun 24/7, providing early warnings. Power companies can temporarily shut down grids to avoid overloads, and satellites can be put into safe mode. Plus, every solar maximum teaches us more about our star's fiery temper, data that could one day help predict these storms like we forecast hurricanes. So while the sun's upcoming tantrum might rattle our tech, It also offers a front-row seat to one of nature's most awe-inspiring performances. And here's the kicker, this cycle might be stronger than expected. Early observations show sunspot numbers already outpacing predictions, hinting at a more active maximum. Whether that means more dazzling auroras or more disruptive flares, one thing's certain: the sun is waking up, and it's got everyone's attention. So keep your eyes on the skies and your phone charged. The next few years could be a roller coaster of solar drama, blending beauty and chaos in equal measure. Hidden in the constellation Aquarius, a dim red dwarf star is quietly hosting one of the most tantalizing planetary systems ever discovered. TRAPPIST-1, barely the size of Jupiter yet packing 7 Earth-sized worlds, has astronomers buzzing with excitement, and for good reason. 3 of these planets orbit snugly in the star's habitable zone, where temperatures could allow liquid water to pool on their surfaces. But the real magic happens when these worlds cross in front of their tiny sun, offering us a fleeting chance to study their atmospheres for the chemical fingerprints of life. These planetary transits are like cosmic eclipses in miniature. As each planet glides across TRAPPIST-1's face, starlight filters through its atmosphere. If it has one, leaving behind telltale absorption lines in the spectrum. It's as if the planets are holding up secret messages written in light, waiting for our telescopes to decode them. Already, observations hint at atmospheres rich in hydrogen or water vapor, though the smoking gun molecules like oxygen or methane that could signal biological activity remains elusive. That's where next-generation instruments come in. The James Webb Space Telescope has already trained its mirrors on this system, peering into the infrared where gases like carbon dioxide shout loudest. But Webb is just the opening act. Upcoming missions like the European Space Agency's Ariel, set to launch in 2029, are designed specifically to dissect exoplanet atmospheres with surgical precision. Imagine a space observatory dedicated solely to sniffing out the chemistry of alien worlds, analyzing hundreds of planetary transits to separate planetary signals from stellar noise. TRAPPIST-1's compact architecture makes it a prime target. Its planets transit frequently, sometimes as often as every 1.5 Earth days, giving scientists a treasure trove of data. What if we find something? Even a tentative detection of biosignatures would send shockwaves through science. These planets are so close together that, standing on one, you might see neighboring worlds hanging in the sky like oversized moons. If life exists there, could it have hopped between them via meteorites, as some theories suggest happened in our own solar system? Or would each world be an isolated experiment in biology, shaped by its unique environment? The system's red dwarf star adds another twist. These planets are likely tidally locked with permanent day and night sides, creating starkly different climates across their surfaces. Yet TRAPPIST-1's greatest gift might be humility. Its planets remind us that Earth-like worlds don't need sun-like stars. Red dwarfs, once dismissed as too tempestuous for life, outnumber all other stars combined, and if they commonly host habitable worlds, the galaxy could be far more crowded with potential homes than we ever imagined. Every transit observed, every atmospheric profile decoded, brings us closer to answering humanity's oldest question. Are we alone under these stars? The answer might already be written in the dim, flickering light of a tiny star 40 light-years away. Remember that strange, cigar-shaped visitor from deep space that whipped past Earth in 2017? Oumuamua, the first known interstellar object to cross our solar system, left astronomers scratching their heads, and it might not be gone for good. While it's currently speeding away into the cosmic void, gravitational forces could slingshot it back toward us in tens of millions of years. But here's the twist: if Oumuamua returns, its next appearance might finally answer the burning questions it left behind. Was it just a weirdly shaped comet, or something far more extraordinary? The mystery centers on Oumuamua's bizarre acceleration as it exited our solar system. Normal comets speed up when their ices vaporize, creating a visible tail, yet Oumuamua had no tail, no detectable gases, and no obvious explanation for its sudden boost. Some scientists theorize it might have been fueled by hidden reserves of hydrogen ice, silently boiling away in the vacuum of space. Others, like Harvard astronomer Avi Loeb, raised eyebrows by suggesting it could have been artificial, a solar sail or debris from an alien civilization. While most researchers lean toward natural origins, the debate reveals just how little we understand about objects born around distant stars. Imagine Oumuamua making a return visit millions of years from now, long after human civilization has transformed or vanished. Future astronomers, whether they're human, AI, or something else entirely, would have technology we can't even dream of to study it. Advanced sensors could scan for molecular clues we missed or even attempt to intercept it. If it's truly a fragment of alien engineering, signs of wear or microscopic structures might finally come to light. More likely, though, it'll prove to be a rare type of dark comet, challenging our definitions of what these interstellar nomads look like. The bigger picture, Oumuamua's journey, hints at how crowded the galaxy might be with unseen travelers. Billions of similar objects could be drifting between stars, occasionally piercing a solar system like ours. Some might carry water or organic molecules, the raw ingredients of life, sown across the cosmos by these silent wanderers. If Oumuamua swings back one day, it won't just be a scientific curiosity, it'll be a test of how far we've come in decoding the universe's secrets. Until then, its fleeting visit remains a humbling reminder. Space is full of surprises, and we've barely begun to explore. In August 2017, astronomers witnessed something unprecedented, a cosmic collision so violent it sent ripples through the fabric of spacetime itself. The event, known as GW170817, marked the first detection of two neutron stars merging in a fiery explosion called a kilonova. And now, scientists predict another such cataclysm could be on the horizon, perhaps in the same galaxy, NGC 4993, where the original merger dazzled telescopes worldwide. This time, with upgraded detectors and sharper instruments, we might witness the aftermath in unprecedented detail, unraveling secrets about the birth of black holes, the creation of heavy elements, and the very nature of gravity. The beauty of kilonovae lies in their staggering energy output. When two neutron stars spiral into each other, their immense gravitational forces crush matter into exotic states, launching jets of material at nearly the speed of light. The collision fuses atoms into heavy elements like gold, platinum, and uranium, literally forging the contents of a jewelry store in seconds. In fact, the GW170817 event is thought to have produced over 10 times Earth's mass in gold alone. Picture that, entire asteroid belts worth of precious metals scattered into space by a single explosion. Future mergers could help us pinpoint exactly how much of these elements are created, rewriting our understanding of where the universe's heaviest atoms originate. But the real game changer this time around will be our enhanced ability to listen to these events. Gravitational wave detectors like LIGO and Virgo have undergone major upgrades since 2017, becoming sensitive enough to catch fainter ripples from farther away. Where GW170817 was detected for about 100 seconds, future mergers might reveal hours of subtle spacetime distortions, tracing the neutron star's final orbits with exquisite precision. And space-based detectors like the planned LISA mission could one day spot these collisions before they even happen, alerting ground-based telescopes to swing into position ahead of the blast. The afterglow of a kilonova is another treasure trove. Last time, telescopes caught a fading fireball glowing with the signature of radioactive decay, a beacon confirming theories about neutron star mergers. Now, with instruments like the Vera Rubin Observatory coming online, we could track these afterglows across multiple wavelengths, from X-rays to radio waves. Each slice of the spectrum tells a different story. X-rays reveal the jet structure, optical light shows the expanding debris, and infrared emissions betray the presence of freshly synthesized heavy elements. It's like dissecting a cosmic crime scene, with every wavelength offering another clue. Perhaps most tantalizing is the chance to catch a merger that defies expectations. Some neutron star collisions might birth a magnetar, a neutron star with a magnetic field a quadrillion times stronger than Earth's. Others could collapse directly into a black hole, leaving behind no debris at all. And if we're extraordinarily lucky, we might witness a merger accompanied by a gamma-ray burst, one of the universe's most energetic phenomena. Each scenario would challenge our models, forcing us to rethink how matter behaves under conditions impossible to replicate on Earth. So while NGC 4993's first kilonova was a milestone, the next could be a revelation. With every upgrade to our detectors and telescopes, we're not just observing these events, we're stepping into a new era of cosmic forensics, where each collision peels back another layer of the universe's deepest mysteries. And when the next neutron stars collide, the entire astronomical community will be watching, ready to decode the echoes of their cataclysmic dance. Proxima Centauri, our solar system's closest stellar neighbor, might seem like the perfect place to hunt for alien life until you witness its violent temper. This tiny red dwarf star, just over 4 light-years away, hosts Proxima b, an Earth-sized planet snug in its habitable zone. But Proxima b's cozy orbit comes with a catch. The star it circles is prone to sudden, devastating eruptions called superflares, capable of blasting the planet with radiation doses thousands of times stronger than anything Earth receives from the Sun. One of these outbursts in 2016 was so powerful, it briefly made Proxima Centauri 10 times brighter, a wake-up call for anyone dreaming of lush landscapes on its orbiting world. What makes these flares so dangerous? Unlike our Sun's occasional tantrums, Proxima Centauri's eruptions are frequent and ferocious, fueled by the star's tangled magnetic fields. Imagine a cosmic lightning storm, but instead of harmless sparks, it's a barrage of X-rays and ultraviolet radiation strong enough to strip away atmospheres. For Proxima b, this means any potential oceans or air could have been slowly cooked away over billions of years, leaving behind a barren rock bathed in deadly starlight. Even worse, the planet is likely tidally locked, with one side permanently facing its angry sun, a recipe for extreme temperature swings that could make life's survival a monumental challenge. Yet scientists haven't given up on Proxima b just yet. Some theories suggest that a thick atmosphere or global magnetic field might shield the planet, diverting radiation like an invisible umbrella. Others point to extremophiles on Earth, organisms thriving in toxic vents or radioactive pools, as proof that life can adapt to unthinkable conditions. The real test will come when next-generation telescopes, like the Habitable Worlds Observatory, analyze Proxima b's atmosphere for signs of chemistry out of balance, hints that something or someone might be weathering the storm. Here's the twist: Proxima Centauri's flares might actually help us spot life. Intense radiation can break apart molecules like water or carbon dioxide, creating detectable byproducts like oxygen that wouldn't otherwise accumulate. It's a cosmic irony. The very eruptions that threaten life could also betray its presence, but time is of the essence. Observations show Proxima b endures these flare-ups roughly every 2 months, meaning any fragile biosignatures might be constantly reshuffled or destroyed before we can spot them. The deeper lesson: red dwarfs like Proxima Centauri outnumber all other stars in the galaxy combined. If their habitable zones are really radiation-soaked death traps, the universe's most common real estate might be far less welcoming than we hoped. Or perhaps life, against all odds, finds a way, clinging to shadowed ice caps or thriving in subterranean oceans. Either way, Proxima b is more than just a potential second Earth. It's a laboratory for testing the limits of life itself, forcing us to rethink what it truly means to be habitable in a universe full of fire and fury. Deep in the heart of our galaxy, something strange is stirring, a cosmic feast that could unfold right before our eyes. Sagittarius A, the Milky Way's supermassive black hole, has spent eons lurking quietly in the darkness. But now it's poised to devour a passing gas cloud, a meal that could ignite fireworks visible across the cosmos. This isn't just another celestial snack. It's a rare opportunity to watch a black hole wake up, flexing its gravitational muscles in ways that could put Einstein's theories to the ultimate test. The star of this drama is a swirling mass of gas called G2, a cosmic wanderer drifting perilously close to Sagittarius A's event horizon. As it spirals inward, tidal forces will stretch and shred it like taffy, superheating the material to millions of degrees. The result, a spectacular light show X-ray flares so brilliant they'll outshine the black hole's usual faint glow by orders of magnitude. Telescopes around the world are already trained on this region, waiting to capture every moment of the destruction. But the real prize isn't the spectacle itself, it's what the flares can teach us about how black holes bend space, time, and even light itself. Einstein's general theory of relativity predicts how gravity should warp the paths of particles near a black hole, but Sagittarius A offers something laboratories never can: a natural experiment in extreme physics. As G2 disintegrates, astronomers will track how its debris swirls into the void, mapping the warped spacetime around the black hole with unprecedented precision. Any deviation from Einstein's predictions, a flicker of light where none should exist, or particles moving just a fraction faster than expected, could hint at new physics lurking beyond our current understanding. It's like watching a cosmic ballet where the dancer's every move reveals the shape of the stage beneath them. The timing of this feast is anyone's guess. Cosmic events don't run on human schedules. Some scientists think the show might peak within the next few years, while others caution it could take decades. But whenever it happens, the data will be priceless. Black holes are famously secretive, hiding their secrets behind event horizons that let nothing escape. G2's destruction gives us a backstage pass, letting us study the forces at work just outside the point of no return. And there's a tantalizing wild card. What if Sagittarius A isn't dining alone? Some theories suggest smaller, hidden black holes could be orbiting the giant like remoras around a shark. If one of these unseen predators intercepts part of the gas cloud, it could trigger secondary flares, a telltale sign of the Milky Way's dark underbelly. Either way, the feast at our galaxy's center promises more than just a light show. It's a chance to peer into the abyss and see what stares back. Out there in the interstellar darkness, beyond the reach of our sun's warmth, a tiny spacecraft is whispering its final words back to Earth. Voyager 1, humanity's farthest-flung emissary, has been traveling for nearly half a century, but its journey is nearing an end. By the 2030s, its nuclear power source will fade, silencing its transmissions forever. Think about that for a moment. This piece of 20th century technology, carrying a time capsule of human culture, will become a silent wanderer among the stars, carrying our message into the void long after we're gone. What makes Voyager 1's mission so extraordinary isn't just the distance it's covered, over 14 billion miles from home, but the legacy it leaves behind. Strapped to its side is the Golden Record, a gold-plated copper disc packed with sounds and images from Earth. There's the laughter of children, the songs of humpback whales, greetings in 55 languages, and even the brainwaves of a woman falling in love. It's a snapshot of our planet, frozen in time, meant for anyone, or anything that might stumble upon it millions of years from now. The record's cover, etched with symbols explaining its origin, doubles as a cosmic treasure map, pointing the way back to a tiny blue dot in the Milky Way. Yet Voyager's true gift to science isn't just its poetic payload, it's the data. As it crossed into interstellar space in 2012, it shattered our assumptions about the boundary between the Sun's influence and the wider galaxy. The spacecraft revealed a turbulent magnetic frontier where solar winds collide with the cold plasma of deep space. Even now, its instruments occasionally wake from hibernation to send back readings about cosmic rays and interstellar dust measurements that ground-based telescopes could never capture. When the power finally runs out, Voyager won't just go dark, it'll become something even more profound. Drifting through the galaxy at 38,000 miles per hour, it'll outlast Earth itself. In about 40,000 years, it'll glide within 1.6 light-years of a star in the constellation Camelopardalis, carrying humanity's artifacts into uncharted territory. The Golden Record's contents might degrade over millions of years, but the spacecraft's metal skeleton could endure for billions, a fossil of human ingenuity in a lifeless cosmos. So while we mourn the impending silence of Voyager's radio, its mission is far from over. It's just entering its most enduring phase, an eternal voyage through time and space, bearing witness to our existence long after our cities have crumbled and our sun has burned out. One day, this humble probe might be the only evidence that we were ever here at all. While Voyager 1 drifts into eternal silence, another spacecraft is screaming toward the exact opposite environment, plunging into the inferno of our solar system's heart. In 2025, NASA Parker Solar Probe will make history by diving deeper into the Sun's corona than any human-made object before it, skimming just 3.8 million miles from the solar surface. That's closer than Mercury's orbit, a region where temperatures soar past 2,500 degrees Fahrenheit and solar winds scream outward at 1,000,000 miles per hour. This isn't just a mission, it's a daredevil stunt in the name of science, pushing engineering to its absolute limits to uncover secrets that have eluded us for centuries. What makes this plunge so extraordinary? The Parker Solar Probe isn't just observing the Sun from a safe distance. It's threading the needle through the corona itself, the star's wispy outer atmosphere where the solar wind is born. Think of it like flying a kite into a hurricane's eye to study the storm's structure, except this hurricane is made of magnetized plasma and stretches across the entire solar system. To survive, the probe hides behind a revolutionary heat shield no thicker than a textbook, coated with white ceramic that reflects 99% of the Sun's brutal radiation. Behind that shield, instruments will operate at room temperature despite the furnace-like conditions outside, like a submarine cruising through molten lava. The data Parker collects could rewrite textbooks. Solar wind, the stream of charged particles that bathes our planet, has puzzled scientists since its discovery. Why does it accelerate to supersonic speeds as it leaves the Sun? How do magnetic fields twist and snap, launching billion-ton clouds of plasma toward Earth? These aren't just academic questions. Understanding solar wind is key to predicting space weather, the cosmic storms that can knock out satellites, disrupt power grids, and even endanger astronauts. Parker's close-up measurements might finally reveal the engine behind these invisible tempests, giving us days or even weeks of warning before the next Carrington-level event strikes. But the probe's most tantalizing target, solving the mystery of why the corona is millions of degrees hotter than the Sun's surface below it, a paradox that defies common sense. It's like walking away from a bonfire and getting burned worse the farther you go. One theory suggests nanoflares' countless tiny explosions might be heating the corona like a cosmic microwave. Another points to magnetic waves rippling through the plasma, transferring energy in ways we don't yet understand. Parker's sensors, dipping in and out of this superheated zone, could catch these processes in action, snapping the equivalent of a high-speed photo of sunlight being born. Every orbit, Parker uses Venus's gravity to slingshot closer to the Sun, each pass shaving off distance like a diver testing deeper waters. By 2025, it'll reach its final, blistering orbit, touching the corona at speeds topping 430,000 miles per hour. That's fast enough to fly from New York to Tokyo in under a minute. And when it does, it won't just be collecting data. It'll be making history as the first object to touch a star, crossing an invisible boundary where the sun's atmosphere begins and solar wind becomes unstoppable. The irony, this mission, which braves temperatures capable of vaporizing steel, is named after Eugene Parker, the astrophysicist who first theorized the solar wind's existence in 1958, back when colleagues dismissed his ideas as fantasy. Now, the very phenomenon he imagined is being studied by a machine bearing his name, a poetic full circle for science. As the probe races toward its date with the sun, it carries more than instruments. It carries the legacy of human curiosity, our relentless drive to reach into the fire and pull out answers. And what it finds might not just illuminate the secrets of our star, but of every star that lights up the cosmos. Beneath Europa's cracked, icy shell lies one of the most promising hiding places for life beyond Earth, a global ocean twice the size of all Earth's seas combined. In the 2030s, NASA Europa Clipper will embark on a daring reconnaissance mission to this frozen moon, skimming just 16 miles above its surface to hunt for signs that life might thrive in its dark, salty depths. This isn't just another planetary flyby, it's a targeted search for cosmic company, probing an alien water world that's been sealed under ice since the dawn of the solar system. The Clipper's strategy hinges on Europa's mysterious plumes, geyser-like eruptions that occasionally blast water vapor and organic material hundreds of miles above the moon's surface. Imagine a robotic detective catching samples of these plumes mid-flight, analyzing their chemistry without ever touching down. The spacecraft's instruments will act like interstellar bloodhounds, sniffing for molecular fingerprints, complex carbon chains, amino acids, or even lipid molecules that could hint at microscopic organisms stirring below. But the plumes are unpredictable, vanishing for years at a time, which is why the Clipper will make nearly 50 close passes, maximizing its chances of a direct encounter with these elusive cosmic fountains. What makes Europa's ocean so special isn't just its water. It's the promise of hydrothermal vents similar to those on Earth's seafloor, where scorching mineral-rich fluids spew from the crust. On our planet, these vents teem with extremophile microbes that thrive without sunlight, drawing energy from chemical reactions rather than photosynthesis. Europa's tidal flexing, caused by Jupiter's immense gravity, likely keeps its rocky core warm enough to sustain similar vents, a potential buffet for microbial life. The Clipper's ice-penetrating radar will map the thickness of the icy crust, while its thermal cameras pinpoint hotspots where warmer ice might betray activity below, like thermal windows into the abyss. Yet the mission's greatest challenge lies in proving any discoveries aren't false alarms. Europa's surface is bombarded by sulfur from Eo's volcanoes and radiation from Jupiter's magnetic field, creating chemical noise that could mimic signs of life. To separate signal from noise, the Clipper will compare plume chemistry across multiple flybys, searching for patterns that point to biological rather than geological origins. It's like trying to distinguish between a campfire's smoke and a wildfire's both burn, but one carries the scent of something more deliberate. Beyond biology, the mission could rewrite planetary science. Europa's ocean interacts with its rocky mantle in ways we've never observed directly, potentially creating underwater volcanoes or mineral towers taller than Everest. Its ice shell, constantly shifting from tidal forces, might host cryovolcanoes that erupt slush instead of lava, or vast subglacial lakes trapped between ice layers. Every reading from the Clipper's 9-instrument payload will peel back another layer of this frozen enigma, revealing whether Europa is a sterile ice ball or the solar system's most promising oasis. Perhaps most thrilling is what comes next. If the Clipper finds compelling evidence, it could pave the way for a lander, a drill-equipped robot designed to melt through the ice and release a submersible into the dark waters below. For now, though, the Clipper represents our best shot at answering one of humanity's oldest questions, whispered across 800 million miles of space: are we alone? The icy moon holds its secrets close, but not for much longer. Every orbit, every scan brings us closer to knowing whether another world right in our cosmic backyard has been harboring life all along. For decades, dark matter has been the universe's most elusive ghost, an invisible presence that sculpts galaxies, bends light, and outweighs ordinary matter 5 to 1, yet refuses to show its face. But that cosmic hide-and-seek game might finally be ending. Deep underground in abandoned gold mines and beneath mountain ranges, a new generation of detectors is poised to catch dark matter in the act, and the results could rewrite the rules of physics as we know them. At the heart of this hunt is LUX Zeppelin, the world's most sensitive dark matter experiment, buried nearly a mile beneath the Black Hills of South Dakota. Picture a titanium tank filled with 10 tons of liquefied xenon, chilled to -148 degrees Fahrenheit, surrounded by layers of shielding to block cosmic rays. It's essentially a high-tech trap waiting for a single dark matter particle to bump into a xenon atom and release a telltale flash of light, the odds of success. Astronomically slim, but if it happens, the discovery would echo through scientific history. What makes this search so urgent? Dark matter isn't just a puzzle, it's the missing framework of the universe. Without it, galaxies spin too fast to hold themselves together, and the cosmos's large-scale structure makes no sense. For years, physicists assumed dark matter was a WIMP, a weakly interacting massive particle left over from the Big Bang. But after decades of empty-handed searches, some researchers are questioning that assumption. LUX Zeppelin represents a last, best hope for WIMP, pushing sensitivity to limits where even the most elusive particles should, in theory, reveal themselves. Yet the real excitement lies in the alternatives. If LUX Zeppelin comes up empty, the door swings wide for exotic possibilities, actions, primordial black holes, or even particles from hidden dimensions. The experiment's very design allows it to test multiple theories at once, like a cosmic fishing net with bait for every conceivable catch, and it's not alone. Across the globe, facilities like Italy's Zeno NNT and China's Panda X are running parallel searches, each refining techniques to eliminate false signals from neutrinos and other background noise. The stakes couldn't be higher. Detecting dark matter wouldn't just fill a textbook gap, it would open a new frontier of physics. Imagine confirming particles that don't interact with light or ordinary matter, yet dictate the fate of galaxies. Or discovering that dark matter has its own periodic table, with diverse forms we've yet to imagine. Some theories even suggest it could be harnessed one day, like a shadowy counterpart to electricity. Of course, failure is a possibility, but in science, even null results are transformative. If dark matter continues to evade detection, it might mean our understanding of gravity is fundamentally flawed, forcing a rethink as radical as Einstein's leap beyond Newton. Either way, the next few years promise answers, and in this game, the universe has held its cards close for too long. The detectors are primed, the scientists are waiting, and somewhere in the darkness, the truth is stirring. Right now, the best images we have of exoplanets are blurry dots, tiny pinpricks of light lost in the glare of their host stars. But in just a few decades, that could change in ways that rewrite our understanding of alien worlds. Imagine staring at the first ever photograph of an exoplanet's surface, where swirling clouds, vast oceans, or jagged mountain ranges come into focus not as artistic interpretations, but as real, tangible landscapes. This isn't science fiction. With next-generation telescopes like the Extremely Large Telescope coming online by 2030, astronomers are on the verge of capturing images so sharp they could reveal continents on planets light years away. The secret lies in the ILT's 39-meter mirror, a colossal eye that will gather 15 times more light than Hubble. Combined with advanced coronagraphs masks that block starlight like a cosmic eclipse, this telescope could isolate the faint glow of a rocky exoplanet, transforming it from a pixelated speck into a detailed map. Picture a world like Proxima Centauri b, its surface split between molten lava flows and frozen wastes under the crimson glow of its dwarf star. Or glimpse swirling storms on a super-Earth where gravity crushes the clouds into bizarre, flattened shapes. But the real prize, identifying liquid water. If the ELT detects glints of sunlight reflecting off alien oceans, it would mark the first time we've seen another world's lakes or seas with our own eyes, proof that Earth isn't the only oasis in the cosmos. Yet the most jaw-dropping possibility lies in the shadows. As resolution improves, unusual geometric patterns, straight lines, repeating structures might hint at something far more provocative than natural terrain. While the odds are slim, an unmistakable grid of city lights or sprawling agricultural belts would spark a debate unlike any in scientific history. The ELT won't have the resolution to confirm alien megastructures outright, but anomalies in its data could flag targets for even more powerful successors, like NASA's proposed Habitable Worlds Observatory. Of course, challenges remain. Even the ELT will struggle with atmospheric interference, and exoplanets are notoriously camera-shy, often drowned out by their star's brilliance. But techniques like optical interferometry, combining multiple telescopes to act as one, could amplify the signal, teasing out details from the noise. Some astronomers even suggest using the sun's gravity as a giant lens, warping light from distant planets into sharper focus. What's at stake goes beyond pretty pictures. Surface features reveal a planet's history. Volcanoes hint at tectonic activity, ice caps suggest climate cycles, and river valleys betray lost atmospheres. A single image could tell us if a world is a frozen wasteland, a waterlogged paradise, or something entirely alien. And if, against all odds, we spot something that defies natural explanation, well, that's when the real conversation begins. By 2040, the blurry dots of today might give way to landscapes that redefine our place in the universe, one pixel at a time. Deep in the quantum foam of empty space, there's a secret dance happening, one that defies everything we know about reality. What looks like perfect nothingness to our eyes is actually a seething sea of virtual particles, popping in and out of existence so fast they're almost ghosts. But what if we could catch one of these phantoms in the act, pinning it down long enough to witness the impossible, particles born from pure nothingness? That's exactly what scientists are now attempting in labs around the world, probing the boundaries of quantum field theory with experiments so precise they border on alchemy. Picture the vacuum of space not as an empty void, but as a cosmic popcorn maker. At any given moment, pairs of particles and antiparticles like electrons and their evil twins, positrons, burst into being, borrowing energy from the universe itself before annihilating each other in a flash. Normally, this happens too quickly to measure, like a magician's sleight of hand. But under extreme conditions, like near a black hole's event horizon or inside an ultra-strong electromagnetic field, these virtual particles can get ripped apart before they can reunite. Suddenly, they're not virtual anymore, they're real, tangible, and carrying energy that wasn't there a moment before. Now, researchers are recreating this phenomenon in the lab using mind-bending tools like ultra-intense lasers. By firing pulses of light so powerful they warp spacetime itself, these experiments aim to shake loose virtual particles from the quantum vacuum, capturing them in detectors before they vanish. It's like shining a spotlight on a shadow and watching the shadow solidify into something you can touch. If successful, the implications would ripple across physics, proving that energy truly can emerge from nothing, so long as nothing is understood as the seething quantum static beneath reality's calm surface. The math behind this is both elegant and bizarre. Quantum field theory treats every particle as a ripple in an invisible, universe-sized field, like waves on an ocean. The vacuum isn't empty, it's the lowest energy state of that field, but even there, the field never sits perfectly still. Instead, it jitters with fluctuations, tiny waves that briefly crest into particles before flattening back out. This is the quantum version of zero energy, not true nothingness, but a balance of positive and negative fluctuations that cancel out on average. The trick is teasing one of those fluctuations out of hiding, like plucking a single wave from the ocean and holding it in your hand. What makes this so revolutionary isn't just the weirdness, it's the practical stakes. If we can control quantum fluctuations, we might unlock technologies that sound like science fiction. Imagine engines that extract energy from the vacuum itself, or materials stabilized by artificial quantum fields. Some theorists even speculate about manipulating these effects to bend spacetime, creating warp bubbles akin to those in Star Trek. Of course, these are distant dreams, but every experiment inches us closer, testing whether the universe's most fundamental rule might be that reality itself is negotiable. Yet the greatest revelation may be philosophical. If virtual particles can be made real, it blurs the line between existence and non-existence, suggesting that something from nothing isn't a paradox, it's how the universe works. The quantum vacuum isn't dead space, it's a creative cauldron bubbling with potential universes that flicker in and out of being. And soon, for the first time, we might have front-row seats to the show. For less than a millisecond in 2007, a pulse of radio waves brighter than 500 million suns shot across the universe, and nobody noticed until the data was found years later. This was the first recorded fast radio burst, one of space's most baffling enigmas. Since then, astronomers have detected hundreds of these ultra-powerful flashes, some repeating in patterns so strange they've fueled speculation about alien civilizations. But now, thanks to cutting-edge observatories and a stroke of cosmic luck, we might finally crack the code behind these interstellar sirens, and the answer could rewrite how we view the universe's most extreme objects. The game-changer came in 2020 when scientists traced a repeating FRB to a magnetar, a neutron star with a magnetic field so strong it distorts atoms into needle-thin shapes. Picture a cosmic lighthouse, but instead of light, it beams bursts of radio waves so intense they outshine entire galaxies for a fraction of a second. Magnetars fit the profile. They're volatile, prone to starquakes that could launch these bursts, and their ridiculous magnetic fields might twist plasma into the perfect antennas to focus radio energy. But here's the catch, not all FRBs come from magnetars, and some repeat in patterns so precise they almost look engineered. That's where next-generation telescopes enter the scene. Facilities like the CHIME Array in Canada scan the entire northern sky daily, catching FRBs in real time. Meanwhile, the Deep Synoptic Array in California combines hundreds of radio dishes to pinpoint bursts with meter-scale precision. Together, they're building a catalog so detailed we can start separating natural phenomena from potential anomalies. Already, patterns are emerging. Some bursts arrive with a telltale splash of lower frequencies first, suggesting they've traveled through dense plasma clouds, possibly the debris of a supernova or the chaotic environment near a black hole. Others show polarization twists, hinting at magnetic fields strong enough to warp spacetime itself. The real jackpot would be catching an FRB in our own galaxy. In 2020, astronomers watched as the magnetar SGR 1935 plus 2015 emitted a radio pulse eerily similar to distant FRBs, but weaker since it was right next door. It was like finding a smoking gun, yet even this breakthrough left questions. Why do some magnetars produce FRBs while others stay quiet? Could there be multiple origins, from colliding neutron stars to evaporating primordial black holes? And what about those bizarre repeating bursts with intervals that defy natural explanations? That's where the alien hypothesis lingers, not as the leading theory, but as a tantalizing wildcard. In 2017, the repeating FRB 12102 raised eyebrows with bursts spaced roughly every 160 days like clockwork. Another, FRB 1800-916, followed a 16-day cycle, active for 4 days, silent for 12. While natural explanations exist like a neutron star wobbling in a binary orbit, the precision is unsettling. SETI researchers have even scanned some FRBs for narrowband signals buried in the noise just in case. Within this decade, new data could settle the debate. Upcoming missions like the Square Kilometre Array, with thousands of radio antennas spanning 2 continents, will detect FRBs by the thousands, mapping their cosmic neighborhoods in unprecedented detail. If most trace back to magnetars, it'll close one of astronomy's greatest mysteries. But if outliers persist, bursts with structures too clean or patterns too precise, it might force us to confront an even bigger question. Are we reading nature's handwriting or something else's? Either way, the answer will redefine what we know about the universe's most fleeting and most powerful signals. Far beyond Earth's rainstorms, on a world where rivers carve valleys into frozen bedrock and dark dunes stretch for miles, the skies are about to unleash a downpour unlike anything in our solar system. Saturn's moon Titan, shrouded in a thick orange haze, operates on a weather cycle straight out of science fiction, one where methane takes the place of water, falling as rain, pooling into lakes and evaporating back into clouds. But this isn't just a curious analog to Earth's water cycle. It's a dynamic, alien monsoon system with seasons so extreme they trigger methane storms capable of reshaping entire landscapes. And right now, as Titan's northern hemisphere tilts toward summer, scientists are bracing for a seasonal shift that could turn this frozen moon into a temporary paradise for exotic chemistry or even life. The rhythm of Titan storms follows a pattern as reliable as Earth's own monsoons, just stretched across a much longer timeline. A single year on Titan lasts 29 Earth years, with each season dragging on for roughly 7. As the moon's axial tilt brings its northern hemisphere into warmer summer sunlight, methane trapped in icy reservoirs beneath the surface begins to vaporize, rising into the atmosphere like steam from a boiling pot. The result, towering methane clouds, some taller than Mount Everest, that eventually collapse under their own weight, unleashing rains powerful enough to carve fresh riverbeds into Titan's water ice bedrock. These aren't gentle showers. Radar images from NASA Cassini spacecraft have already captured evidence of past storms so intense they left behind flooded plains the size of small countries. What makes these downpours so fascinating is how they mirror Earth's hydrology, but with a twist. On our planet, water evaporates, condenses, and falls in a continuous loop that sustains life. Titan's methane cycle behaves similarly, only at temperatures so cold, -290 degrees Fahrenheit, that water is frozen solid, and methane takes on the role of both liquid and vapor. Imagine standing on Titan's surface during a storm. The sky would weep droplets of liquefied natural gas, pooling into shallow seas like Kraken Mare, a body of methane and ethane larger than the Caspian Sea. The humid air might even carry the scent of organic compounds, a byproduct of sunlight breaking apart atmospheric methane and nitrogen to form complex molecules like vinyl cyanide, a chemical that, on Earth, is used to make plastics but on Titan could form the membranes of alien cells. The real kicker, these methane monsoons might be more than just a spectacle. They could be the engine for Titan's most tantalizing possibility, life. Not life as we know it, but organisms adapted to liquid methane the way Earth's microbes thrive in water. Some scientists speculate that Titan's subsurface ocean, locked beneath an icy crust, could host hydrothermal vents similar to those that support extremophiles in Earth's darkest depths. Others suggest that the moon's surface lakes, constantly replenished by seasonal rains, might foster methane-based biochemistry, a shadow ecosystem that metabolizes acetylene or ethane instead of glucose. The upcoming NASA Dragonfly mission, set to launch in 2027, will land a drone-like rotorcraft on Titan to sniff out these very possibilities, sampling the organic, rich soil and perhaps even catching a methane shower in action. Yet Titan storms also pose cosmic riddles. Why do some methane lakes appear and vanish with the seasons while others persist for millennia? How do the moon's winds, which move sluggishly due to Titan's thick atmosphere, manage to sculpt dunes the size of skyscrapers? And could lightning sparked in those churning methane clouds catalyze the formation of even more complex organic molecules? Every storm is a natural laboratory testing the boundaries of chemistry in conditions we've barely begun to understand. As Titan's summer approaches, telescopes worldwide will train their lenses on this hazy moon, watching for the telltale shimmer of fresh rainfall. Each droplet that falls carries more than just methane. It carries clues to whether life can arise in the unlikeliest of solvents under the faint glow of a distant sun. So while Earth's weather may feel familiar, Titan's monsoons remind us that nature's imagination is boundless, and that somewhere under an orange sky, it might be raining the building blocks of a biology we've yet to dream of. Somewhere in the depths of space, the faintest whispers of the universe's most violent encounters are still echoing not in sound, but in ripples of space-time itself. When two black holes collide, they don't just vanish into the cosmic background. Their merger sends gravitational waves surging across the universe like ripples in a pond, distorting the very fabric of reality. For years, we've detected these waves using observatories like LIGO, but there's a catch. We're only catching the final moments, the last desperate spirals before the black holes become one. Now, a new generation of telescopes is preparing to listen for something far more elusive, the echoes of these ancient collisions, reverberations trapped in the afterglow of the Big Bang itself. These echoes aren't the gravitational waves we've grown familiar with. They're secondary tremors, space-time distortions that ricocheted off the turbulent plasma of the early universe and lingered in the cosmic background like ghostly fingerprints. The key to unlocking them lies in the cosmic microwave background, the faint glow left over from when the universe was just 380,000 years old. Hidden within that microwave static could be subtle imprints from primordial black hole mergers, events so ancient they occurred before the first stars flickered to life. Next-generation telescopes like the Big Bang Observer and the Einstein telescope, with sensitivities 100 times sharper than current detectors, could tease out these faint signals, transforming our understanding of cosmic dawn. What makes this search so revolutionary? Those echoes aren't just cosmic noise, they're time capsules. The way space-time rings after a black hole collision depends on the shape of the black holes themselves. If echoes from the early universe deviate from the patterns we see today, it could mean the first black holes weren't born from dying stars as we assume, but erupted directly from the chaos of cosmic inflation. Some theories even suggest these primordial black holes could be the elusive dark matter we've been chasing, hiding in plain sight by warping space-time instead of emitting light. The implications ripple across physics. If we confirm echoes from mergers older than galaxies, it would prove black holes existed before stars did, a concept that upends our timeline of cosmic evolution. It might also reveal whether the early universe was a fractal of microscopic black holes, or if space itself once vibrated with frequencies we can't yet imagine. The echoes could even carry scars from exotic physics, evidence of extra dimensions or quantum gravity effects imprinted during the universe's first frantic seconds. But here's the catch: separating these whispers from the cosmic microwave background is like trying to hear a single raindrop in a thunderstorm. It requires detectors chilled to near absolute zero, orbiting beyond Earth's noisy magnetic field, and algorithms trained to recognize patterns no human has ever seen. Yet the payoff could redefine cosmology. Every echo decoded would be a snapshot of the universe in its infancy, a moment when black holes, those enigmatic destroyers of light, might have been the architects of everything we see today. We're on the verge of tuning into a cosmic symphony older than time, one where black holes aren't just the end of stars, but the echoes of creation itself. And when those whispers finally break through the noise, they won't just tell us how black holes merge, they'll reveal how the universe learned to sing. Deep beneath the icy crust of Ceres, the solar system's largest asteroid and smallest dwarf planet, lies a hidden ocean of briny water, and it's getting ready to make a dramatic appearance. Scientists now predict that within the next decade, this unassuming world could unleash a cryovolcanic eruption from its mysterious Arcata crater, spewing plumes of salty water high into space. This isn't lava like we know on Earth, but a bizarre, slushy mix of water, ammonia, and salts kept liquid by the dwarf planet's internal heat. When it happens, this eruption will give us our closest look yet at the inner workings of ocean worlds, not just on Ceres, but potentially on Europa, Enceladus, and other icy bodies across the cosmos. What makes Arcata crater the prime location for this spectacle? NASA's Dawn spacecraft, which orbited Ceres from 2015 to 2018, found this 57-mile-wide impact basin glowing with bright salt deposits, the telltale sign of recent geological activity. The most striking feature is Cerealia Facula, a central dome where minerals like sodium carbonate have bubbled up from below, painting the crater floor in otherworldly whites and blues. These salts aren't just pretty, they're clues. On Earth, similar deposits form around hydrothermal vents, places where mineral-rich water emerges from underground reservoirs. On Ceres, they suggest the crater sits atop a pressurized chamber of liquid brine, straining against its icy ceiling like a shaken soda bottle. The mechanics of a Cererian cryovolcano would be unlike anything in our terrestrial experience. Instead of molten rock, picture a slow-motion geyser erupting in the near vacuum of space. With surface temperatures hovering around -100 degrees Fahrenheit, the brine would partially freeze as it sprays outward, creating a mist of ice crystals that could rise miles high before settling back to form fresh, bright patches. Some scientists speculate these eruptions might happen in cycles, driven by tidal forces from Jupiter's gravity or internal heat from radioactive decay. Others think impacts could trigger them, cracking the crust and releasing pent-up fluids, meaning the next asteroid strike could kickstart the show. Why does this matter beyond scientific curiosity? Ceres brine isn't just water. It's a cocktail of organics and salts that could mimic the conditions where life first emerged on Earth. The sodium carbonates in Arcata crater are particularly intriguing. On our planet, these minerals help stabilize amino acids, the building blocks of proteins. If similar chemistry is happening deep in Ceres' ocean, it raises the tantalizing possibility that even this small, dark world might harbor the ingredients for life. Future missions could sample these erupting plumes directly, testing for complex molecules without ever needing to drill through ice, just as we've done with Enceladus' famous jets. Timing the next eruption is the challenge. Cryovolcanic activity seems to come in fits and starts, with some models suggesting Ceres might experience major outbursts every few million years. But given the fresh appearance of Arcata's deposit, some possibly just centuries old, we could be entering a window of heightened activity. The upcoming European Space Agency's Hera mission, while focused on asteroid deflection technology, might catch Ceres at the right moment if it passes close enough. More dedicated missions are being proposed, including orbiters with infrared spectrometers to monitor heat signatures and subsurface radars to map the brine reservoirs in real time. When the eruption does occur, it won't just be a scientific bonanza, it'll be a cosmic spectacle. Salt plumes erupting in sunlight could create temporary bright spots visible to amateur telescopes, like tiny stars flashing on the dwarf planet's surface. More importantly, the composition of these plumes will serve as a direct sample of Ceres' underground ocean, revealing whether it's a sterile brine or a brew rich with prebiotic chemistry. Either way, this small world is about to remind us that in the search for alien oceans and perhaps life itself, sometimes the most promising places come in unexpectedly small packages. Buried in a vault beneath the University of Washington, a 6-foot-tall copper cylinder hums silently, its supercooled heart tuned to catch whispers from a ghost. This is ADMX, the Action Dark Matter Experiment, and it's hunting for one of the universe's most elusive phantoms actions. These hypothetical particles, lighter than electrons by a factor of 1 trillion, could solve 2 cosmic mysteries at once: the true nature of dark matter and why the universe didn't annihilate itself in a burst of antimatter moments after the Big Bang. If actions exist, they're streaming through you right now, invisible and unfelt like a cosmic breeze. ADMX isn't just waiting for them, it's listening. The genius of the experiment lies in its simplicity. Actions, if real, should occasionally transform into microwave photons when they pass through intense magnetic fields. ADMX creates precisely those conditions inside its chilled cavity, where a powerful magnet stands ready to amplify this faint signal. Think of it like tuning a radio to a frequency no station has ever used, hoping to catch a song composed at the dawn of time. The detector's sensitivity is staggering. It could spot an action converting to photons even if the event occurred just once every 10 years in the entire volume of the cavity. That's like detecting a single grain of sand dropped into the Grand Canyon from space. Why bet on something so intangible? Actions emerged from an elegant solution to one of particle physics' great puzzles. Why the strong nuclear force which glues atomic nuclei together doesn't seem to care about the direction of time. Most interactions at this scale should violate what's called charge parity symmetry, yet they don't. In 1977, theorists Roberto Pexi and Helen Quinn proposed actions as the missing piece particles that would subtly tweak the strong force's behavior, restoring balance to the equations. Decades later, physicists realized these same particles could also be dark matter, drifting through galaxies like an invisible fog that only gravity can touch. The hunt isn't limited to ADMX. Across the globe, experiments like CAP in South Korea and Haystack in the U.S. are probing different action mass ranges, each refining techniques to eliminate false signals. Some use quantum squeezing to reduce noise, others deploy multiple cavities to scan faster. Meanwhile, astrophysicists scour white dwarf stars and neutron stars for excess X-rays that might betray actions decaying in their intense magnetic fields. Even the cosmos itself acts as a laboratory. If actions permeate galaxy clusters, their subtle interactions with light could leave faint imprints on the cosmic microwave background, a fingerprint waiting to be decoded by next-generation telescopes. The stakes go beyond dark matter. Actions could rewrite the early universe's history. If they oscillated in just the right way during cosmic inflation, they might have tipped the scales against antimatter, explaining why anything exists at all. Some models even suggest actions could form bizarre, planet-sized clumps called action stars, or seep through Earth to trigger unpredictable nuclear decays. Others theorize they might interact so weakly that detecting them would require turning the entire moon into a detector, a project already sketched in speculative papers. What happens if ADMX hears the action song? Overnight, a hypothetical particle would become real, reshaping physics from the ground up. Laboratories would pivot to study its properties, telescopes would retune to map its distribution, and theorists would scramble to explain how it fits into the larger quantum puzzle. But silence wouldn't mean failure. Every frequency ruled out narrows the search, and some of the most inventive ideas like action, wind, pushing on sensitive pendulums or lasers probing quantum vacuums wait in the wings. The action hunt embodies science at its most daring, chasing shadows with instruments of exquisite precision, guided by math's whisper that something beautiful must be out there. Whether ADMX finds them or not, the quest itself reveals how much universe remains hidden in plain sight, and how clever we've become at teasing its secrets loose. Beneath the rusty surface of Mars, something unexpected is stirring, a seismic whisper that could rewrite everything we know about the red planet's hidden heart. NASA InSight lander, perched on the barren plains of Elysium Planitia, has been eavesdropping on Mars quarks since 2018, and the tremors it's recorded are about to reveal Mars' deepest secret, the true nature of its core. This isn't just planetary science, it's a detective story spanning billions of years, one that could explain why Mars transformed from a warm, wet world into the frozen desert we see today. The clues lie in how seismic waves travel. On Earth, quakes send vibrations ricocheting through layers of crust, mantle, and core, each bending or slowing the waves in telltale ways. Mars, though quieter, operates similarly. InSight's ultra-sensitive seismometer has detected over 1,000 Mars quarks, some so faint they'd go unnoticed without the lander's precision instruments. But a handful of stronger events, like the magnitude 5 quake in May 2022, sent waves plunging deep enough to graze the edges of the core. The way those waves emerged on the other side of the planet holds the key to Mars' innermost mysteries. Here's the breakthrough. By timing how long these waves take to traverse Mars, scientists can deduce whether the core is solid or molten, or something stranger. Early data suggests it's not just liquid iron, as once assumed, but a swirling mix of lighter elements like sulfur and oxygen. That changes everything. A lighter core would have cooled faster, shutting down the planet's magnetic dynamo earlier in its history. Without that protective magnetic shield, solar winds would have stripped away Mars' atmosphere like sandblasting a fresco, leaving the surface barren and radiation-scarred. In essence, the core's composition could be the reason Mars died while Earth thrived, but the plot thickens. Some Mars quarks originate not from tectonic shifts, but from magma moving deep underground, hinting that parts of Mars might still be geologically alive. If true, it raises the staggering possibility that residual heat in the core could one day be tapped to warm subterranean habitats for future colonists. Even more tantalizing is the chance that Mars' core holds clues to our own planet's fate. Earth's magnetic field isn't immutable. It's flipped polarity countless times and could weaken again. Understanding why Mars' dynamo sputtered out might help us predict, or even prevent, a similar crisis here. The final act of this revelation is still unfolding. InSight's solar panels, now dust-choked, have ended its mission, but the data it beamed back will fuel discoveries for years. Upcoming missions, like the Japanese-led Mars Moon's exploration, plan to deploy even more advanced seismometers. And as algorithms sift through InSight's recordings, they might uncover fainter quakes that slipped initial detection, each one a new thread in the tapestry of Mars' hidden history. So while the red planet's surface appears frozen in time, its core tells a different story, one of ancient catastrophes, unexpected resilience, and secrets buried so deep, it took a robot geologist with a seismometer to tease them loose. What we learn here won't just illuminate Mars, it'll remind us how fragile a planet's life support systems truly are, and how lucky we are that Earth's heart still beats strong. The universe plays a dangerous game of cosmic dodgeball, and Earth isn't always the winner. Consider this: in 2017, an interstellar visitor named Oumuamua zipped past Earth at nearly 200,000 miles per hour, closer to us than Mars orbits the Sun. What if, instead of a near miss, it had been a direct hit? The chilling truth is we might not have seen it coming until days before impact. Unlike local asteroids that loop predictably around the Sun, rogue objects like Oumuamua arrive unannounced from the void between stars, moving so fast they give astronomers almost no time to react. Let's crunch the numbers. Statistically, an Oumuamua-sized object roughly a quarter-mile long strikes Earth once every 10 million years. But here's the catch: that estimate assumes we've spotted all the threats, which we haven't. Current telescopes like Pan-STARRS in Hawaii excel at tracking near-Earth asteroids, but interstellar objects travel on wild, unpredictable paths. By the time one enters our solar system, it's already too close for comfort. In Oumuamua's case, astronomers had just 19 days to study it before it vanished into the depths of space. An object on a collision course might give us even less warning, possibly just hours, if it approached from the sun's glare where telescopes are blinded. So how would we defend ourselves? Traditional asteroid deflection methods like NASA's DART mission, which nudged a space rock off course in 2022, rely on years of advance notice. Against an interstellar bullet, we'd need something faster and far more forceful. One radical proposal involves prepositioning nuclear-tipped interceptors in space, ready to launch within hours. A well-placed detonation could vaporize part of the object's surface, creating a jet of plasma that acts like a natural thruster to push it off course. Another idea, laser arrays that fire concentrated beams to ablate the surface over months, gently steering it away, though this requires detecting the threat impossibly early. The wild card in all this composition, Oumuamua's bizarre acceleration hinted it might be made of exotic hydrogen ice or even a porous, lightweight structure unlike any local asteroids. If future interstellar projectiles share these traits, they could shatter unpredictably when hit, turning a single massive impactor into a shotgun blast of debris. That's why newer projects like the Vera Rubin Observatory coming online in 2025 prioritize scanning the entire sky nightly, hunting for fast-moving dim objects that don't belong. Yet the ultimate lesson isn't about fear, it's about humility. Oumuamua was a wake-up call, proving our cosmic neighborhood gets more foot traffic than we imagined. Every unidentified streak in the sky could be the next visitor or the next threat. And while the odds are slim, the stakes are everything. The same vastness that makes these impacts rare also makes them nearly impossible to see coming. A reminder that in the grand casino of the cosmos, Earth might be riding a lucky streak that can't last forever. Imagine stepping outside one night and seeing a star where none existed before. A brilliant new pinprick of light flaring to life in a familiar constellation. This isn't just a fantasy, it's a cosmic inevitability. Sirius B, the dense, Earth-sized ember orbiting the brightest star in our night sky, is a ticking time bomb. Quietly, invisibly, it's siphoning gas from its companion star, Sirius A. And one day, when it steals just a little too much, this white dwarf will erupt in a thermonuclear fireball so bright, it'll outshine every star in the Milky Way for weeks. What makes this scenario so chillingly plausible? White dwarfs are the corpses of stars like our Sun's stellar remnant so dense, a teaspoon of their material would weigh as much as an elephant. Normally, they cool quietly over billions of years, but when a white dwarf has a close stellar companion, as Sirius B does, it can pull hydrogen from its neighbor's atmosphere. This stolen gas piles up on the dwarf's surface, compressed by gravity until it reaches a critical temperature and pressure. Then, in a heartbeat, the entire accumulated layer detonates in a runaway fusion reaction, a nova. The result is a blast visible across interstellar distances, like a cosmic flashbulb popping in the darkness. Sirius B is particularly primed for this spectacle. Located just 8.6 light-years away, practically next door by galactic standards, it's one of the most scrutinized white dwarfs in the sky. Observations show it's already accreting material from Sirius A, though at a slow rate. The ticking clock here depends on subtle changes in that flow. If the transfer speeds up even slightly, perhaps due to shifts in Sirius A's stellar winds, the dwarf could reach its explosive tipping point within centuries rather than millennia. When it happens, the nova would shine with the intensity of a crescent moon, casting faint shadows on Earth and outshining every planet in our sky. The aftermath would be a goldmine for science. Nova don't just light up the cosmos, they forge heavy elements like carbon, nitrogen, and oxygen, scattering them into space like cosmic confetti. Telescopes would analyze the explosion's light curve in real time, tracking how elements form in the fireball's wake. Spectroscopy could even reveal whether Sirius B's detonation triggers a shockwave through the surrounding interstellar medium, compressing nearby gas clouds and potentially jump-starting new star formation. But here's the twist: this eruption wouldn't destroy Sirius B. Unlike a supernova, which obliterates its progenitor, a nova leaves the white dwarf intact, ready to repeat the cycle. Given enough time, Sirius B could explode again and again, a cosmic heartbeat pulsing across the eons. And while we might not witness its next outburst, the inevitability of such events across the galaxy hints at a universe far more dynamic than it appears. Every flicker of a nova is a reminder that even the quietest stars are capable of sudden, spectacular violence, and that the night sky's calm facade is just an illusion. Picture this: two particles separated by light years of empty space, locked in an impossible dance where changing one instantly alters the other, no matter the distance. This bizarre phenomenon, called quantum entanglement, has been proven in labs across Earth. But what if we stretched this connection across stars? Scientists are now sketching blueprints for an experiment so audacious it could redefine the limits of reality itself, entangling particles on Earth with counterparts orbiting distant suns, creating the longest quantum link in history. The setup sounds like science fiction, but the physics is rock solid. When particles become entangled, their properties like spin or polarization remain mysteriously synchronized. Measure one, and its partner instantly adopts a correlated state, even if it's on the opposite side of the galaxy. Einstein famously dismissed this spooky action at a distance as impossible, yet countless experiments have confirmed it's real. Now, researchers want to push this effect to cosmic scales by embedding entangled photons in laser beams fired toward spacecraft near Alpha Centauri or beyond. Those photons, arriving years later, would still be invisibly tied to their Earth-bound twins, a living test of whether quantum bonds truly defy spacetime's rules. But here's where it gets thorny. While entanglement allows instantaneous correlation, it can't transmit information faster than light, at least not in any way we've discovered. The moment you measure one particle, its entangled partner snaps into a predictable state, but you can't control what that state will be. It's like having two magic coins that always land on the same face, no matter how far apart they're flipped, but you never get to choose whether they show heads or tails. This limitation keeps entanglement from becoming a galactic Morse code for now, yet the experiment's real value lies in probing quantum mechanics foundations. If entanglement holds over light years, it would seal our current understanding of quantum theory. But if the link breaks, if particles suddenly stop sinking across vast distances, it could hint at undiscovered physics, like hidden dimensions or a universal decoherence field that erases quantum weirdness at large scales. Some theorists even speculate that spacetime itself might emerge from a deeper quantum substrate, making entanglement the true fabric of reality. A cosmic scale test could reveal cracks in our cosmic wallpaper. Practical challenges loom, of course. Maintaining entanglement requires shielding particles from any interaction that could collapse their quantum state, a tall order when firing lasers through interstellar dust and magnetic fields. Proposed solutions include quantum error-correcting codes or using photons encoded in specific frequencies that resist cosmic interference. And let's not forget the time lag. A probe at Alpha Centauri would take over 4 years to receive its entangled photons, turning each experiment into a generational endeavor. But imagine the payoff. Success wouldn't just be a Nobel Prize, it would open a window into the universe's most profound secrets. Are quantum connections truly universal, or do they fray at cosmic distances? Could we one day engineer quantum networks linking colonies across star systems, enabling unhackable encryption, or telescopes with baseline widths measured in light years? The answers might lie in those fragile beams of light carrying the universe's strangest handshake between the stars. So while faster-than-light communication remains a dream, this experiment would achieve something equally revolutionary, testing whether the threads binding reality itself can stretch across the unimaginable void, or if somewhere in the darkness between stars, even quantum magic has its limits. Somewhere beneath the icy plumes of Enceladus or buried in the Martian soil, the first whispers of alien life may already be calling out to us, not with radio signals or flashing lights, but through the quiet chemistry of microscopic organisms. The search for extraterrestrial microbes isn't just a scientific endeavor. It's a race against time and technology, one that could culminate in the most profound discovery in human history within our lifetime. While we scan distant stars for signs of intelligence, the breakthrough might come from a robotic arm scooping dirt on Mars or a spacecraft skimming through the geysers of Saturn's tiny moon. Consider Enceladus first. This icy moon spews towering plumes of water vapor from a hidden ocean, and those jets are packed with organic molecules, carbon chains that serve as life's building blocks. The upcoming Europa Clipper mission will fly through similar plumes at Jupiter's moon Europa, but Enceladus remains the prime candidate for a more targeted life detection mission. Picture a probe equipped with a mass spectrometer, diving through those icy fountains like a cosmic hummingbird, tasting the water for amino acids or lipids molecules that don't just hint at habitability, but at actual metabolism. The smoking gun would be an imbalance in chemical ratios, like an excess of right-handed amino acids over left-handed ones, a signature that can't easily be explained by geology alone. Mars, on the other hand, offers a different kind of hunt. The Perseverance rover is currently collecting tubes of sediment from an ancient river delta in Jezero crater, where microbial mats might have flourished billions of years ago. Those samples, destined for return to Earth by the early 2030s, could contain fossilized bacteria, tiny spirals or filaments preserved in rock, like the earliest life on our own planet. But there's a tantalizing wild card. What if something is still alive down there? Subsurface brines or deep caves could harbor extremophiles clinging to existence, microbes that adapted to Mars' harsh radiation by retreating underground. A future drill mission capable of reaching those hidden pockets might not just find fossils, it could revive them. The implications of such a discovery would ripple far beyond science textbooks. Confirming life, even in microbial form, on another world would prove that biology isn't a fluke of Earth, but a fundamental feature of the cosmos. It would mean life arose not once, but at least twice in our solar system alone, suggesting the universe is teeming with organisms we've yet to meet. Philosophers and theologians would grapple with the meaning of our place in creation, while policymakers would scramble to draft planetary protection laws to prevent contamination between worlds. And for the average person, the realization that we're not alone, even if our neighbors are single-celled, would trigger a paradigm shift as profound as Copernicus displacing Earth from the center of the universe. Yet the real challenge lies in proving it. A microbe on Mars might share ancestry with Earth life, blasted into space by an ancient asteroid impact, making it a cousin, not a true alien. To settle the debate, scientists would need to find life with a radically different biochemistry, perhaps using arsenic instead of phosphorus in its DNA, or a genetic code with more than 4 base pairs. Enceladus, isolated in its icy shell, offers a cleaner test. Any life there would have evolved independently, a second genesis untouched by Earth's biology. And then there's the quiet, unsettling possibility that we'll find the ruins of life, chemical traces of organisms that once thrived but went extinct when Mars dried up or Enceladus' ocean froze. Even that would rewrite history, painting the solar system as a graveyard of abandoned experiments. Either way, the machines we're sending now are more than robots. They're messengers on the verge of answering a question as old as civilization itself. Are we the universe's only children, or just the first ones to start looking for our siblings? The clock is ticking. Within the next decade, a vial of Martian soil or a vial of Enceladus spray could land in a lab on Earth, its contents about to shatter our cosmic solitude. And when that day comes, the universe will feel both infinitely larger and strangely more intimate. a place where life, in all its fragile tenacity, refuses to be lonely. Most of us think of the universe's end as a slow fade, stars burning out, galaxies drifting apart, everything cooling into darkness. But what if the finale isn't a whisper but a scream? Enter the Big Rip, a hypothesis so violent it makes black holes look gentle. Picture this: 22 billion years from now, an invisible force grows so powerful it doesn't just push galaxies away, it tears them apart atom by atom. First, galaxy clusters are ripped to shreds, then solar systems, then planets. Finally, in the last fractions of a second, atoms themselves are wrenched apart, their protons and electrons torn asunder by a force even the strong nuclear bond can't withstand. This isn't science fiction, it's a plausible cosmic apocalypse, and scientists are racing to find proof it's coming. The key player here is dark energy, the mysterious force accelerating the universe's expansion. Right now, its grip is weak enough that gravity still holds galaxies together. But if dark energy's strength isn't constant, if it grows over time, as some theories suggest, it could eventually overpower every force in nature. Think of it like a rubber band stretching. At first, it resists, but pull hard enough and it snaps. In the Big Rip scenario, space itself becomes that rubber band, stretched until even the tiniest particles can't hold on. The hunt for clues is already underway. Telescopes like the Dark Energy Survey and the upcoming Euclid spacecraft are mapping the universe's expansion with millimeter precision, searching for any sign that dark energy is changing. One telltale hint would be an acceleration rate that doesn't just stay constant but increases, a hallmark of so-called phantom energy, the most extreme form of dark energy. Another clue might come from the cosmic microwave background, the afterglow of the Big Bang. Subtle distortions in its pattern could reveal whether dark energy's push has been intensifying since the universe's infancy. But here's the twist: even if the data leans toward a Big Rip, it wouldn't mean doom is certain. Some models suggest dark energy might peak and then diminish, like a wave cresting and breaking. Others propose that quantum effects could stabilize space before the rip reaches catastrophic levels. And then there's the wild card of undiscovered physics, perhaps a deeper layer of reality that kicks in to halt the unraveling. The chilling beauty of the Big Rip isn't just its violence, but its inevitability if the math holds. Unlike other cosmic doomsday scenarios, which depend on variables we can't yet measure, this one follows a clear, testable path. Every new measurement of supernova, every galaxy survey, every probe of the cosmic web brings us closer to knowing whether the universe is destined for a slow fade or a spectacular shattering. And while 22 billion years is an unimaginable stretch of time, the answer to how it all ends might be hidden in data we collect within this century. So while we'll never witness the universe's final act, we might soon know its script, whether the cosmos bows out quietly or goes out with the loudest explosion physics allows. Either way, the discovery would redefine our place in the grand story of existence, casting humanity as the fleeting observers of a drama whose final act defies all intuition. The universe might not just fade away, it could tear itself apart, and we're the generation poised to uncover that truth. From the explosive finale of Betelgeuse to the quantum whispers of entangled particles spanning star systems, we've journeyed through 25 cosmic events that could redefine reality as we know it. Each one isn't just a spectacle, it's a scientific revolution waiting to happen. Imagine witnessing the birth of a black hole in real time, or decoding the chemistry of an alien ocean on Europa. Picture telescopes capturing the first surface details of an exoplanet, or dark matter finally stepping out of the shadows. These aren't distant dreams, they're milestones on the horizon, each holding the potential to rewrite textbooks, shatter assumptions, and answer questions that have haunted humanity for centuries. Think about the implications. A single supernova could reveal how gold fills the universe, while a cryovolcanic eruption on Ceres might expose the raw ingredients of life. The merger of two neutron stars isn't just a light show. It's a cosmic forge creating elements we wear as jewelry and rely on in technology. And what if Proxima Centauri's violent flares actually help us spot life clinging to survival under its crimson glow? Every event on this list is a thread in the grand tapestry of discovery, weaving together astrophysics, biology, and even philosophy. But here's the real magic: you don't need a telescope to be part of it. Every one of these breakthroughs will unfold in real time, shared across the globe in images, data, and gasps of collective awe. Whether it's a faint radio burst from deep space or a new Martian rock sample cracking open in a lab, these moments belong to all of us, the curious, the dreamers, the ones who look up and wonder. So now it's your turn. Which event electrifies your imagination? Is it the cosmic detective work of decoding gravitational echoes, or the heart-stopping possibility of spotting city lights on an exoplanet? Drop your pick in the comments and join the conversation. And if you're hungry for more mind-bending wonders, hit subscribe, because the universe never stops surprising us, and neither will we. The cosmos is writing its next chapter, and you've got a front row seat. Don't miss a single revelation.